All right, hey there, Lorenzo. How are y'all doing? Okay. I want to go ahead and get started. Number one, um, on Monday we were talking about assignment 23, and we left off in the middle of talking about problem number five. Um, So I want to know, did we get problem number five resolved? Did we figure it out, or do we need to go? Do we need to continue to look at problem number five? Hello.
Can you finish it, please?
Okay. Let's pick up where we left off. Um, so problem number five, we left off right here, and I believe what we had just done was. Oh, we were working to make the second element in row two a zero. So we did some work, and this is the work that we did right here, and we made this a zero. So the next thing that we want to do is we want to make the second element in row three a zero. So here's what we're going to do. You can see right here, I said don't erase. Um, so just like I did up here to make this 5 a 0 by multiplying row 2 by negative 5, I'm going to take negative 21 times row 2 and add it to row 3. Alright, so here we go. This is going to become 0. That becomes 0. Alright, so negative 21 times a negative 1/3. 1/3 of 21 is 7. A negative times a negative is going to be positive. So that's going to be a positive 7 minus 1. That becomes 6. And then same thing here. Um, 1/3 of 21 is 7. Negative times a negative is positive. And that means that um, we still get a, we're going to get a 6 right here also. Alright, still good? So what I would do at this point is I would take 1/6 of row 3. So we'll come right up here. We'll still have 0, 1, 0, 2/3, comma, negative 7/3. 0, 1, negative 1/3, negative 1/3, and then 0, 0, 1, 1. And now what we want to do is we want to make the elements above this 1 in row 3 become 0. We want this and this to become 0. So here's what I would do. I would take 1/3 of row 3 and add it to row 2. And at the same time, I'm going to take negative 2/3 of row 3 and add it to row 1. So here we go. First of all, row 3 does not change. Alright, so here we go. You're going to get 0 because you're multiplying by 1/3 by 0. That's going to become 0. You're still going to get a 1 right there. This becomes 0. Alright, here we go. That's going to become 0 as well. Okay. Hopefully we are on the right track. I don't have my answer key up. We're about to find out. Then you're going to get 1, 0, 0. Alright, 2/3 times 1 is going to be a negative 2/3. Added to negative 7/3 is going to be a negative 9/3. Negative 9 divided by 3 is a negative 3. That leads us to the solution. Hopefully we did everything right. That x is equal to negative 3, y is equal to 0, and z is equal to 1. I think that does it for us. Is that the answer and the enter key? Yeah. It's always a little bit scary coming out at the end, seeing if you did everything right, but there it is. There is our solution. So, did we encounter fractions in our work? Yes. We did encounter fractions, but we can work with the fractions and everything works out fine. Now, one thing that, I guess I'm going to not say what I was thinking I'm going to say. I'm just going to leave it as it is. There is problem number 5. Okay, so in terms of the rest of that assignment 5, how are we doing? Did we finish it? Yeah? Good. Alright. So, what we want to do at this point is we want to start looking at assignment 25. I sent out an announcement that I have the notes for assignment 25. They are just blank notes. Do y'all have an opportunity to get those printed off? Okay. What we're going to do with the rest of our time today is that we're just going to go through and I'm just going to talk about these examples in the assignment 25 notes. We're not going to get through all of them. It's not going to happen. What's going to happen is I'm going to just get through at least half of them. I'll get through at least half of them. And then what I'm going to do is I'm going to make a nice copy of my notes. I don't know, maybe I'll just give you my copy and let you look at it. That may save me a little bit of time. It's not the nicest writing, but it gets the job done. And whatever I do, I'm going to give you the completed version of my notes because I'm just not going to have time to make the videos. And so in the meantime, after today's lesson, you're going to need to take a look at my notes and hopefully I can arm you with enough information to tackle the entire homework. We're not going to do all the examples, but I'm going to arm you as much as I can so that you can take a look at my work that I've already done for the notes once I post those, and you can see, oh, this is how he did that, and that. So let's go ahead and get out our notes for assignment 25, and let's get started. All right. Assignment 25, nonlinear systems and systems of inequalities. A nonlinear system is a system that contains at least one equation that cannot be expressed as the form ax plus by equals c. This is a linear equation. So we're going to have a system where something is not linear in your set of equations. So if you take a look at these two examples that I have right here, this equation right here is linear. We know it's linear because the exponent on x is 1, the exponent on y is 1. That's going to create a line. But if you look at this equation, we have the x squared. Well, anytime you start introducing an x squared, and as long as your coefficient of y is 1, this becomes quadratic. So we're dealing with a quadratic equation and a linear equation, and we want to look for the solution to this system. Similar example over here, we have another quadratic equation. We have an x squared and a y to the first degree. But down here in equation 2, both the x squared and the y are being squared. This turns out to be a circle. We're going to be looking at the graphs of these systems to help us visualize the answers, but you can see that a nonlinear system has equations, an equation or equations that are not linear. But we're going to be using the same type of methods, substitution and the addition method, to solve these systems. So let's go ahead and get started. We're actually going to be taking a look at this example up here. I want to switch colors. As normal, I like to label my equations. And we want to solve this system using the methods of substitution and addition. Now, again, the way I approach something may not necessarily be the way that you approach something. But when I look at this system, I notice that my coefficient in front of my y is a 1. In this case, it's a negative 1. I think that it would be the easiest thing to do would be to take equation 2 and solve for y. Let's work to get y by itself. So how do I get y by itself? I can start off by adding or subtracting the 3x on both sides. And then I can divide the entire equation by a negative 1, so we get y is equal to a 3x minus 9. Now what we can do is we can go to equation 1, which is x squared is equal to 2y plus 10, and we can substitute this expression for y into this other equation. This is the substitution method. So we're doing the same type of work that we did with linear systems. It's just now that we have some nonlinear equations. So what do we get? We get x squared is equal to 2 times 3x minus 9 plus 10. Make sure that you put that 3x minus 9 in parentheses because we have to recognize that that 2 is going to distribute. And now, look what kind of equation that we have. We now have a quadratic equation. Well, how do we solve quadratic equations? We start off by setting that equation equal to 0. So, let's see, let's go ahead and combine like terms. Negative 18 plus 10 is going to be a negative 8. Then set this equal to 0. We get x squared minus 6x plus 8 is equal to 0. So we now want to solve this equation. How do we solve this? Well, I would use factoring. What are the factors of 8 that add up to a negative 6? How about a negative 2 and a negative 4? So then once you set each factor equal to 0, you get x is equal to 2 and x is equal to 4. So this is something new. I now have two solutions for x. X at the same time is 2 and 4. Those are my solutions. So that means that for each of these solutions, I have to go through and find the corresponding y. So here's what we're going to do. For x equal to 2, I'm going to use this very nice equation for y. Y is equal to 3x minus 9. That means that y is equal to 3 times 2 minus 9. That means that y is equal to 6 minus 9. That's a negative 3. So we get the solution to negative 3. There is one solution to the system. But remember, we had two values for x. So we have to go through and do the same thing for x equal to 4. We're going to plug this into y is equal to 3x minus 9. So y is equal to 3 times 4 minus 9. 3 times 4 is 12, minus 9 is 3. Y is equal to positive 3. So what is our solution? Our solution is 4, 3. So we have two solutions to the system. Now, you want to check. You want to make sure that both solutions work. So let's just go back up here to this quadratic equation. X is 2, y is negative 3. 2 squared is 4. Okay? 2 times negative 3 is a negative 6. Negative 6 plus 10 is 4. 4 is equal to 4. Check. Second solution, 4, 3. 4 squared is 16. 2 times 3 is 6. 6 plus 10 is 16. 16 is equal to 16. Both these solutions check out. So here are our solutions to the system. Now, something that I didn't emphasize a whole lot with systems of equations, at least in our homework, we did it in the notes a little bit, but looking at the visual solution. So let's hop on over to a graphing utility, Desmos in this case, and let's type in these equations. X squared is equal to a 2y plus 10. So there's our parabola. And then the second equation is 3x minus y equals 9. And there's the line. So can you see that that line is crossing through that parabola? And it's crossing that parabola at 2 points. I'll have to lift this up so you can see those, but those 2 points are 2, -3, and 4, +3. There's your visual interpretation of the solution to this system. Okay, does that make sense? Alright, in the last class, in my 9 o'clock class, I did example 2. So why don't you go back and you can watch the lecture video in the 9 o'clock class over example 2 to see what I did in example 2. Okay? I don't want to repeat it if I've already done it. So you can watch that video from the 9 o'clock class for example 2. Same thing for example 3. I've already done this problem in the 9 o'clock class, so go to the 9 o'clock video to watch me work out this example. I did not do example number 4. So let's do example number 4 together. In this problem, as I look at this system, you might be thinking to take the x squared plus 3 and substitute it in for the y down here. I really don't want to do that because what that will end up doing is, notice that this is a y squared. You would have to end up squaring x squared plus 3. That's going to create a 4th degree expression, and I just don't want to deal with a 4th degree expression. So I have another thought up my sleeve, and that other thought would be to eliminate my x squareds. And why is that a good thought? Well, notice that both of these, the coefficients in front of both of these x squareds is a 1. So let's do a little bit of work here. I think I kind of want to have, we'll call this equation 1 and equation 2. I would kind of like to have these equations at least be somewhat similar in terms of having the x's and the y's on both sides. So if I take equation 1, y is equal to x squared plus 3, I could move that x squared over to the other side, so I have negative x squared plus y is equal to 3. And then we could take equation 1 and add it to equation 2. So you have negative x squared plus y is equal to 3. Then that's x squared plus y squared is equal to 9. And we're going to add these two together. So you can see what we're doing here, we're doing an elimination. We're using the process of elimination to solve this system. So our x squareds cancel out, they're gone. Now I can't add y and y squared together, so all I can say is that I have y squared plus y is equal to 3 plus 9 is a 12. Now what do we have? We have a quadratic equation. We have a quadratic equation in terms of y. How do we solve quadratic equations? Well, we start off by setting them equal to 0. And then I would say, can I factor this? Can I factor this quadratic equation? Sure. The factors of negative 12 that add up to a 1. How about y plus 4 times a y minus 3? Y plus 4 times a y minus 3. which then is going to lead us to the conclusion that y is equal to negative 4 and y is equal to a positive 3. So we have two solutions for y. Now we have to go and find the corresponding values of x for each y. Does that make sense? For each y, you got to find the corresponding x. So let's do that. Let's see. Let's just start off. For y is equal to negative 4, we have that y is equal to x squared plus 3. So we have negative 4 is equal to x squared plus 3, which then means we have negative 7 is equal to x squared. Now that's a negative 7, so when you square root both sides, you're going to end up with an imaginary number. You're going to end up with x is equal to plus or minus I times the square root of 7. Now, one of the things that we have here is this. We have imaginary answers. And I didn't have time to ask anybody, but do we include imaginary answers in our solution sets? Yes or no? Graphically it's not going to make any sense, but we could go ahead and throw that solution in there. Our solutions, so far we have I squared root of 7, comma, negative 4, and then negative I squared root of 7, comma, negative 4. But we still have to go through and do the same work for y equal to 3. So for y equal to 3, we have y is equal to we have 3 is equal to x squared plus 3. Subtract the 3 on both sides, so 0 is equal to x squared. And this is pretty straightforward. You get x is equal to 0, so you get the solution 0, 3. So here are our solutions. Now, I have to go back and look at the answer key for the homework. I can't recall if we have any imaginary solutions. One textbook that I looked at said we'd throw those imaginary solutions out. The other textbook that I said included the imaginary solutions. So I don't know. Do we put them in or do we leave them out? So at this point, let's just put them in. But let's take a look at this graphically, just for a second. Number one, this is a parabola. Y equals x squared plus 3, we have a parabola. And this is a circle. Now, when I think about this, if I just draw a circle, I can draw a parabola through this. Here's 1, 2, 3, 4 solutions. I could have a circle where I have a parabola doing this. There's 1, 2 solutions. Or I could have a circle and a parabola doing this where there's only one solution. I think this is going to be a situation that we're going to encounter here. Let's take a look. So over in Desmos, let's start off with that. Let's start off with the circle. X squared plus y squared. Oops, got it. Add the plus. Plus y squared equals 9. Equals 9. So there's our circle. And then our parabola, y is equal to an x squared plus 3. There, can you see it? There's only one solution at 0, 3. There's only one real solution to this problem. Okay, back to our notes. Same thing with problem number 5. This is on the 9 o'clock video, so watch the 9 o'clock class video for problem number 5. So this little section concludes the nonlinear systems. Now we're going to look at systems of inequalities. So let's just start off here with a quick review. Graphing x is less than or equal to 3. What does that graph look like? Well, if I put 0 right here and 1, 2, 3 right there, we know how to do this on a number line. If it's less than or equal to 3, I'm going to put a circle around 3. I'm going to shade to the left, and because of the or equal to, I'm going to put a solid circle around the 3. That's what that would look like on a number line. And we know how to do this. Well, what if we do the same type of work now on a coordinate plane? What would this look like on a coordinate plane? Well, you still have your number line across the x-axis. So if this is 3, we could think about putting a solid circle around 3. And yeah, you would be shading that part of the number line. But since we're on a coordinate plane, we're not just talking about x values now. We're talking about x and y values. So we had to think about including all of the points that would be to the left of that line, x equal to 3. So this is the line x equals 3. So we're talking about all of the ordered pairs that would be in this shaded region. We're talking about that ordered pair, we're talking about that ordered pair, and that one, and that one, and that one, and all the infinitely many numbers, infinitely many coordinates over in this shaded, what's called a half plane. That's what we're talking about. So we're going to transition from shading on a number line to now shading on a coordinate plane. So let's take a look at this example 6. What would the graph of y greater than -4 look like? Now a couple of things I want to make note of. Notice that there is no or equal to part of this inequality. We use a solid line when we deal with the or equal to part. We're going to use a dotted line when there is no or equal to. Now, what does the line y equal to -4 look like? Well, we got to come down here to y equal -4. And this is going to be a horizontal line. So we're going to draw a dotted horizontal line. Now, what's greater than -4? Well, -3, -2, -1, 0, 1, 2, 3, everything above this. So we don't just shade the line, we shade every single, all this shaded region in what is called, again, a half plane. We're talking about every single ordered pair that would fit in this half plane. That's what the graph of y greater than negative 4 looks like. Okay, so now we've done this with nice little things like x is less than or equal to 3 and y is greater than negative 4. Let's take a look at some linear equations. Graph and shade y is greater than negative 2/3 x. So because of the strictly greater than, we're going to use a dotted line. I want to take a look at this equation, y is equal to negative 2/3 x, and I want to think about it for a second. We want to compare to y is equal to mx plus b. So m is our slope, that's a negative 2/3, which means we're going to go down 2 and to the right 3. My y-intercept b is 0, so that means my starting point is at 0, 0. So let's just start getting a sketch of what this line looks like. We're going to start at 0, and I go down 2 over 3. I can go up 2 to the left 3. Now, remember, we're going to use a dotted line. Let's see if I can get that dotted line. There we go. Now, y is greater than. Now, greater than means that just like you had a greater than up here, it means you're going to shade above the x-axis. So, above the line. Not above the x-axis, above the line. So what's above the line? Well, it's this region right here. Now, a sure way to check this is to pick a test point. So what's a point that's in this shaded region? Well, there's lots of points. For this purpose, I'm going to pick the point 1, 1. Now, if I plug in 1, 1 back into my original equation, I should get a true solution. Or true statement. Test 1, 1. So is 1 greater than negative 2/3 times 1? Is 1 greater than a negative 2/3? Well, yeah, that checks out, doesn't it? What if I pick a test point over here? What would this be? This would be 2, 3. Negative 2, 3. What if I test negative 2, 3? That's that point right here. Is it in the shaded region? Yes. So is 3 greater than negative 2/3 times a negative 2? Is 3 greater than 4/3? Well, 4/3 is 1 1/3. So yeah, that's true. You could even pick counterpoints. You know, if you pick the point negative 2, 0, that should give you a false statement. Negative 2, 0. Y is 0. Negative 2/3 times a negative 2 is going to be a positive 4/3. 0 is not greater than 4/3, so you know that that point is not satisfying the inequality. So that's what we're going to be doing for a few examples. So let's look at example number 8. Graph and shade 2x minus 3y. So this is what we want to do to get started is we want to basically rewrite as y equals mx plus b. So I have negative 2x minus 3y is greater than or equal to 6. So if I subtract the 2x on both sides, that becomes negative 3y is greater than or equal to negative 2x plus 6. Now we have to divide everything by negative 3. Now what happens when you divide an inequality by a negative? Yes, you're exactly right. The signs are going to change. This becomes less than positive 2/3 x minus 2. So, looking at this, my slope is a positive 2/3. My b is a negative 2, so that means my starting point is at 0, negative 2. Let's shade. So we're starting at 0, negative 2. And a couple of quick things. Number one, the or equal to means we're going to use a solid line. And our slope is 2/3, so we're going to go up 2 over 3. Down 2 over 1, 2, 3. Let's use a solid line to draw the line between these points. Now, look at this. This says y is less than. So that means when you have the less than, that means you're going to shade below. Shade below. So just to verify this, let's pick a test point. I like easy test points, so let's pick that test point at 0, negative 4. If I test 0, negative 4, we have 2 times 0 minus 3 times the negative 4 should be greater than or equal to 6. So that's 0 plus 12 greater than or equal to 6. 12 is indeed greater than or equal to 6. Check. So that's a quick way to test, hey, do I shade above or below? Plug in a test point. Test point checks out. You know, if I put the counter test point in 0, 0, 0, 0 is not greater than 6, so that's why it's not above. So we shade the half plane below. We have to shade the half plane below. Alright, I think I got time to get maybe 2 more examples in. Let's do this one. This one's interesting because we're not dealing with a line anymore. This is a circle. That's a circle. So remember when we compare to the standard form of a circle, x minus h quantity squared plus y minus k quantity squared is equal to r squared. Well, I could rewrite this as x minus 0 quantity squared plus y minus 0 quantity squared is equal to 3 squared, which then tells me that my center is at 0, 0, and my radius is 3. So let's graph that circle. And it's strictly less than, so we're going to use a dotted line. So here's my center at 0, 0. We need to go up to 3, across the 3, down 3, over 3. Alright, let's do our best circle impression. Oh man. There we go. I got an eraser. I can clean that up a little bit. There you go. There's my circle. Now, less than. Man, where do I shade? Do I shade out here or do we shade on the inside? Well, pick a test point. What is the easiest thing to pick on the inside? The easiest test point that I find is 0, 0. 0 squared plus 0 squared, is that less than 9? Yes. So pick an easy test point to prove for yourself that you're going to shade on the inside. If you want a counterpoint, a counterpoint would be, maybe 4, 0. So then you have 4 squared plus 0 squared less than 9. Is 16 less than 9? No, that's false. So that's why you're not shading on the outside. Does that make sense? Alright. So that's how we shade or graph inequalities. Let's talk about a system of inequalities, and I think I'll be able to get one example in. Here, we want to graph and shade the system of inequalities. So, let's get started. We have equation 1 and equation 2. Let's start off with equation 1. We have x minus y is less than 1. Well, we want to rewrite this in a form that we can graph with. So if I start solving for y, we get negative y is less than negative x plus 1, which then means that y is now, we're going to divide by negative 1, change the direction of your inequality. Y is greater than x minus 1. I'm just going to highlight this for right now. My slope, m, is equal to 1, and my y-intercept is at 0, negative 1. And then equation 2, we have 2x plus 3y is greater than or equal to 12. So that becomes 3y is greater than or equal to a negative 2x plus 12. Divide everything by 3, we get y is greater than or equal to a negative 2/3 x plus 4. I'm just going to circle that and make some quick notes. My slope is a negative 2/3, and my y-intercept is at 0, 4. So let's go through and do some work. First line, y is greater than x minus 1. So we're going to start off at negative 1. And my slope is 1, so we have this up 1 over 1, up 1 over 1 kind of thing happening. Down 1 over 1, down 1 over 1. And we have a dotted line. Now, before you shade, because we don't want to shade this whole entire region, what you want to do is you just want to make note of what is going to get shaded. So it's greater than, so we're going to shade above it. So I put these little arrows right there to tell me that I'm shading above this region. So think about shading that region. In fact, let's just go ahead and do it. Let's just shade that region. Because I got an eraser. You don't shade it. I don't know if you've already shaded it. Sorry. But I intended for you not to shade this. Now let's graph this line. We start at 4. 1, 2, 3, 4. And I'm going to go down 2 over 3. So down 2 over 3. down to over 3. We're going to use a solid line to graph that line. And this is greater than, so we're going to shade this area. But we want it to know, since we have a system, we want to know what shaded area
Your conference is
satisfies
scheduled to
both
end in 2 minutes.
inequalities. So the only shaded area that we're really concerned about is this shaded area right here. This is the shaded area that satisfies both inequalities. So this is kind of why I didn't want you to shade, but I did. Think about erasing this, and the only shaded area that satisfies both inequalities would be this area right here. If you pick a test point in this area, like 3, 3, if you test 3, 3, 3 minus 3 is 0, which is less than 1, check. 2 times 3 is 6, 3 times 3 is 9, 6 plus 9 is 15, it's greater than 12, check. This point in this shaded region satisfies both inequalities. If you pick test points in these other shaded regions, they wouldn't satisfy both. Alright. So in my closing minutes, seconds, I'm going to work to get a completed, nice copy of my notes out and post it to Blackboard. Maybe it'll happen today. Hopefully it'll happen early tomorrow. And on Friday, I hope you'll have time to start addressing the homework. We can address any remaining questions over assignment 25. And I think it'd be a good idea if we have a quiz on Friday as well. So,
Your conference is now over. Goodbye.
Take care. Bye-bye.